Welcome to Geometry with Mr. McCall. Be sure to like the video and subscribe to my channel for more math content. Hey everybody, today we're going to be talking about how do you derive the volume of a sphere formula, which we've already discussed is 4/3 pi r cubed. The main tool that we're going to be using to do this is called Cavalieri's principle. This is kind of a precursor to some integral calculus methods that aren't really that important right now. But as you saw from the other video, basically the idea is if you have two solids that have the same height, and you have these corresponding cross sections of those solids that have the same area, you can conclude that the two solids have the same volume. So again, if the cross sections have the same area, that means that these solids have the same volume. So what you saw in the video was kind of a little bit of a quick version of this, but I'm going to go through the details of how exactly the cross sections do have the same volume. So our first thing we have over here is a cylinder that has both a radius of r and a height of r. So I kind of like to think of it as like a square cylinder because the height and the radius are the same. Then we have inside of it a cone, an inverted cone because it's going upside down like that, which has a base equal to the base of the cylinder and the same height. So a feature of this cone is that if you create any circular cross section of it, the distance right here labeled h, the distance from the base of the cylinder to the circle itself is going to be the same as the radius. And that kind of goes with why the cylinder was square in that sense, with the radius being the same. So this will be congruent as well. I know my drawing's not quite to scale, but just bear with me. If we look at the hemisphere, a hemisphere is just a half sphere. I've drawn the whole sphere, but we're only going to care about this top half of it right here. The sphere has a radius r as well. So this is r, and then the entire height of the sphere, if you want to call it that, would also be r. So in that sense, we've already met the condition that the two solids have the same height. So the height of the hemisphere is r, the height of the cylinder is r. The cross section is going to have a radius, and I put a big R here because it depends on how high up we go. If we had the height all the way down here at 0, the cross section would just be the base of the sphere, or a circle with radius r. And if we went all the way to the top, it'd be like a really tiny circle. But if we have somewhere in between, we can use a Pythagorean theorem to find r like this. So in question, the two solids that we care about are a cylinder that has an inverted cone kind of cut out of it, and the hemisphere. And we're going to use Cavalieri's principle to show that those two are the same. So basically, we need to algebraically show that the ring structure here that I've made with this green circle has the same area as the cross section from the hemisphere. And they have to be the same at the same time. So depending on the height, we want the areas to be the same. So let's look at the cone cylinder system first. To find the area of this ring, we're going to find the area of the cylinder's cross section and then subtract the cone's cross section because that equates to us kind of cutting this hole out of the middle. The cylinder's cross section is always going to be the same because it's a consistent circle the whole time. So that's easy. It's just going to be pi r squared. Now, the radius of the cross section of the circle depends on how high up it is, but the height and the radius of the circle's cross section will both be h, so its area will just be pi h squared instead. If we subtract those two, we get pi r squared minus pi h squared, which leaves us, if I factor out just pi, gives us pi parentheses here, r squared minus h squared. So this is the cross section of just the cone cylinder system. If we move on to the hemisphere, it's going to be a little bit easier. So this time we have this radius big R, I'll call it, because it's a different radius than the radius of the sphere. You can tell it's a little bit shorter. But because the sphere has this radius that goes out in all directions, I can draw a radius here and use the Pythagorean theorem to find big R in terms of the radius of the sphere and the height up that it is. This height and this height are going to be the same. That's kind of how we're going to make this satisfy Cavalieri's principle. So let's begin. So we know that the area of the circle is pi big R squared. So we need to find big R. Let's use the Pythagorean theorem to do that. So we know that little r squared, because that's the hypotenuse, little r squared equals big R squared plus h squared. We want big R squared so we can slot it into this equation. So we're going to subtract h squared from both sides. So that leaves us with r squared equals big R squared equals little r squared minus h squared. So I can take this part. I'm going to replace the r squared in my original equation with it. So that means that we have pi, and I'm going to replace it with this part, r squared, little r squared minus h squared. So here's the cross-sectional area of our cone cylinder ring, and here's the cross-sectional area of our hemisphere. Since they are exactly the same, that means that Cavalieri's principle holds, and these two solids have the same volume. The two solids in question are a cylinder that has this cone cut out of it, because we're only doing the rings, and a hemisphere, which is a half sphere. So what that means is, since we've studied this earlier, we know that a cone takes up a third of the cylinder. So that means that the volume of this cone cylinder part is going to be, if we do the whole cylinder first, the area is pi r squared times r, so that's pi r cubed. Since the cone takes 1/3 of it, the remaining part would be 2/3. So 2/3 pi r cubed is the volume of both of these, a hemisphere and the cone cylinder system. Now, since we want the whole sphere, that means we just need 2 copies of it. So I want one up and one down, and that will equal our final 4/3 pi r cubed, which is exactly what we said it was at the beginning. So basically, by cleverly cutting these into cross sections, we managed to show that two things that appear quite different actually do have exactly the same volume, and then use that to our advantage to show that the volume of a sphere is indeed 4/3 pi r cubed. Again, I always found it strange that something like the volume of a sphere has such a clean representation as 4/3, and it seems like a pretty random fraction, but everything works out in the end.